Are there any questions from last time other than when the exams are returned, I will go over them in class. I'll go over the solution to each problem so you can see how you've done. I'll probably, as you know, the next exam is already scheduled. I believe it's second week in November. And so I'd like to have 2 review sessions before then. Those review sessions, again, I scheduled them for Greg 320. That's where I'll be with the TAs, but it will all be Zoom for you. And that's where I go over any of the homework problems that you would like to work through, the ones in the book or the ones that I assigned. And again, hopefully those prepare you for the exams. Any online questions? No. So last time, I guess we need a screen. Last time we were talking about acceleration of fluid masses. And the initial slide was basically showing you when you have an acceleration, you start to see, if anything, from your own experience, how all of a sudden our original horizontal fluid surface is inclined. And that's a direct result of the acceleration field that we're putting into the system. And so before we looked at fluid statics and the only acceleration field was gravity. And now what we want to do is add on to that an additional gravitational field. When does this happen in practice? You know, if you have a tanker truck and it's taking a corner, you've got an additional acceleration field. If it's decelerating or accelerating, if you're taking some type of a panel and moving it up or down, filled with a fluid, obviously these all affect all of the infrastructure which needs to support and work around those systems. So it is not uncommon to have to work with additional acceleration fields. And the key here is that there's a finite fluid volume. So we're not talking the universe, we're just talking something that we're trying to contain and control. So again, before, in our fluid static situation, we had relative equilibrium. So all the particles were kind of just sitting there. There was no relative motion between particles or relative motion between particles of the walls of, say, the container. Now we're going to have the same thing. Even though we have these accelerations, we're also going to have the fact that there's no relative motion between particles or particles in the boundary. Why? Because when you have relative motions, you get shear stresses. Those shear stresses add additional forces into the system. When we talked about fluid statics before, ultimately we started with a little differential cube, and we just said that the sum of the forces in any direction is 0. When you have relative motion between particles or between particles in the walls, you introduce other forces, shear forces. We didn't account for those before. We're not going to account for them then. Why? No relative motion. Later in the semester, we're going to relax this and actually calculate these forces. So again, we continually build on what we've done in this course. So just as we did before with fluid statics, what we're going to have is some kind of an acceleration field. So this is an acceleration. Think of that first slide where the bartender was sliding the beer glass down the bar. In that case, all you had was horizontal acceleration. But the acceleration field can be in the x, y, or z direction. Basically, what we did before in fluid statics was just say that we only really need to look at the x and z directions because we had gravity collinear with the z. And so whatever happens in the x as a horizontal direction is going to be the same that's happening in the y as far as a horizontal direction. So as we did before, what we do is we take this differential cube that's dx by dy by dz. So we're only doing a 2-dimensional derivation, and we're only going to look in the x and z directions, and then at the end we're going to say, well, whatever happened in the x happens in the y. And then, as we did before with fluid statics, we assume that the pressure varies as you move through the system. It's exactly what we did before, and you have the exact same terms. So if we had P1 on the left-hand side, on the right-hand side, you'd have P1 plus the pressure gradient as you move through the x direction. times the distance you went through. And how we explained this before in fluid statics was you drive from here to Florida for spring break. I don't want to be the bearer of bad news, but spring break has been canceled. You probably know that already. So that's what we're going to do to keep you from leaving and coming back with COVID in the spring. No more spring break, but I think they're giving you 2 3-day weekends as if that makes up for it. So when you drive from here to Florida for spring break, if the temperature gradient was 10 degrees every 1,000 miles, and it's 2,000 miles from here to Florida, then it should increase temperature 20 degrees by the time you get down there. And you could actually calculate the rate per mile. So in this case, again, for every unit that we go in the x direction, we multiply that unit by the gradient, dp dx. And that gives us basically a change in pressure due to the fact that we moved through the x direction from one place to the other. Before, when we did this, we found out there is no change in pressure in the horizontal direction. But again, now we have this acceleration field, and we have to start again right back at the beginning. And if it's 0, it will cancel out like it did before. And then just as we did before in the z direction, we're going to go from some base pressure at the bottom to some pressure at the top, which is that base pressure at the bottom plus the pressure gradient in the z direction times the distance we went through. So the pressure gradient stays the same in the z, and we just increase the pressure change the more and more we move in the z. So again, this term is basically change in pressure as we move in the z direction, and it would indicate the change in pressure from the very bottom of the system all the way to the very top of the system. And in this case, the system is this differential cube. And so don't forget, this cube has a mass, and that mass is, as you did before, would be the density of the fluid times the volume of the container, or the volume of the fluid itself. So that mass is just going to be density times volume. The volume of this cube is dx dy dz. Okay, busy slide. So up in the upper right-hand corner of this slide is that definition sketch. I know it's really small text here, but it's the same sketch we had on the previous slide. So we go from one side to the other, and we have a pressure change as we go through the x direction. Same thing happens when we go from the bottom to the top. We're going to have a different pressure from top to bottom. And so in the x direction, what we're going to do is, now use this equation. In statics, we said sum of forces were 0. Now when we have these finite fluid volumes subjected to an acceleration field, the sum of the forces in any directions is mass times acceleration. The mass is the mass of the cube that's being accelerated. The acceleration field, again, as I drew on the previous slide, that might be your total acceleration. In this case, it has a component in the x and a component in the z direction. And it could even have a component in the y direction. Again, we're just saying x and y are going to have the same results. So when we say that, what are the forces? The forces would be the body forces. So that would be the pressure on one side times the area. Pressure on a submerged plane surface. And this is a differential side, so that pressure P1 on the left-hand side is going to be fairly uniform over that side, which is dz by dy or dz by 1. Since we're just looking at a two-dimensional derivation. And then on the other side, again, we have this pressure that is the original pressure plus that change in pressure because we moved across the x direction. So in the next equation, this is where you see the force on the left-hand side, let's call that F1, is just P1 dz. Again, that's per unit of distance into the y direction. If you just assume that into and out of the paper, that's the y direction, and we're only going in 1 unit, then it's basically P dz times 1. If we did a 3-dimensional derivation, it would be P1 dy dz. And that's the area of the left-hand side. And then on the right-hand side, if we call this F2, here's F2. And first, our sign convention is that x is positive to the right and z is positive upwards. And that's consistent with what we did with fluid statics. And so on the left-hand side, F1 is directed in the positive x direction, so it has a positive sign in front of it. For F2, it's directed in the negative x direction, and so you have a minus F2. And F2 is the pressure on the left-hand side, P1 plus dP dx dx, times the area of the axis, dz dy, or dz in this case for a two-dimensional derivation. And you can see when you subtract F2 from F1, you're just left with the pressure gradient times the area of the side, dP dx times, actually I said the area of the side, what I meant to say is the volume of the cube. So dx dz represents the two-dimensional volume of the cube. So that's the sum of the forces. Now we have to talk about the other side of the equation, and that's mass times acceleration. So again, sum of the forces in the x direction is equal to mass times acceleration in the x. In the x direction, as I indicated on the previous slide, the mass is just the density times the volume. And if you recall from fluid properties, rho g is equal to the specific weight, so rho is density, g is acceleration due to gravity, or density is specific weight over gravity. So on the previous slide, for this term I used density, but again, density is specific weight over gravity. And it's just convenient to have it in that form because it's going to cancel out with something as we move forward from this. So this term is the two-dimensional mass, and all we did was expand MAX to look like this. And then, as you can see, we equate the sum of the forces, minus dP dx dx dz, to MAX, gamma over g dx dz ax. And the first thing you should see is that when we equate these two, the volume of the element, as it always does in these derivations, cancels out. So dx dz is on both sides, it's going to cancel. The volume cancels, and what that lets us arrive at would be the next slide. And in the next slide, when we cancel out the volume, we get minus dP dx, which is the pressure gradient in the horizontal direction. That's the physical meaning of it. When we talked about fluid statics, we said dP dx was 0. No change in pressure if you move horizontally. Think of the fluid surface. What's the pressure on top of the fluid surface? It's atmospheric, everywhere, no matter where you go. If you go some distance h below the surface, what's the pressure there? No matter where you are, it's gamma h. The PDX was 0 in fluid statics. But now, what we just derived was, if you have an acceleration field that has a horizontal component, ax, then as you move horizontally, there's a pressure gradient. Which means if you move horizontally, you're changing pressure. And you already knew this from the first slide in today's lecture. If you thought of that beer glass, I know that's all you can think about now. You had this sloping surface, right? If you moved horizontally from here into the fluid, you're moving into deeper and deeper depths of fluid in this case. You're changing pressure just by moving in the x direction. So again, you already knew this from the first slide. All I did was put mathematics to it, calculus to it. What we're trying to do in here is figure out, one, pressure distributions, but two, how to ultimately get a force from this so that we can design something. So this is what we just found out. And again, if there is no horizontal direction, no horizontal acceleration, then that right-hand side just goes to 0, and again, that's an old friend. This is fluid statics. When you don't have any horizontal acceleration, you get what we had before. No change in pressure as you move in the horizontal. No pressure gradient in the horizontal. So the only time you're going to see changing pressures when you move horizontally in these fluids is if you have a horizontal acceleration. No horizontal acceleration, no change in pressure when you move horizontally. So if there is a horizontal acceleration, then this equation defines how pressures will change. And again, I never hold you to derivations, but it's important you understand how we get to the final equation so you know when you violate the assumptions going into those equations. So ultimately, we're going to integrate this no differently than how we did fluid statics, which gave us P is equal to gamma H. That's where we're going. Some simple equation that we can put to use. So again, if there's horizontal acceleration, you must be changing pressure as you move through the fluid. And I have to underscore this. I've mentioned it before from the very first time we defined what a fluid is. A fluid is a continuum. So if you were looking at that sloping surface of beer, and you started in the fluid and started moving through the fluid and you went into the atmosphere, you no longer have a continuum once you moved into the atmosphere. Okay? So these equations are only good for when you're in the continuum, in the fluid of interest. So again, our definition of what's happening is up in the upper right-hand corner. We have an acceleration field, and we're looking at this differential cube and the fact that pressures change when you move horizontally or vertically. So in this pressure field, we're now looking at the vertical direction and the fact that we do have a vertical component of acceleration in addition to gravity. And so what we will do is take the pressures on the top and the bottom, multiply them by the areas they work over in order to get them into forces such that we can resolve now in the vertical direction, sum of the forces is equal to mass times acceleration. All in the x, all in the z direction. Positive z is upwards. So, as we did before, for the sum of the forces on the bottom, we have this pressure P2, and it acts over an area dx by dy. dy is into the board, or if we're just looking at the two-dimensional area, it's just dx. So P2 dx is the pressure force on the bottom acting upwards, and it's a force, and it's acting in the positive or upwards direction, which is consistent with what we said our coordinate axis system is defined. On the top, we have not only P2 that was on the bottom, but some change in pressure, dPdz times the distance we went through, delta z. Again, dPdz is the pressure gradient in the vertical, and dz is the distance we went through. So that's the pressure on the top. This entire term is the pressure on the top. And then again, we multiply that by the area it acts over to get a force. In two dimensions, the area it acts over is just dx. So it's on the top, the pressure distribution is on the top. It's acting in the negative z direction, and so it has a negative sign in front of it. So if you want, this could be, for example, F3 from P2 on the bottom, and this is F4 from P2 plus dP dx dx on the top. So this would be F3 minus F4. And in the vertical, we always have to remember weight occurs. In some problems, we say ignore the weight, but in this case, we're not going to ignore the weight. And so the weight of this cube is the specific weight times the volume of the cube. Just like the mass of the cube is the density, mass per unit volume, times the volume. Weight is specific weight per unit volume, times the volume. So the weight in this case, we can expand that term on the next line, but it's just going to be gamma dx dy dz in 3 dimensions, or gamma dx dz in 2 dimensions. So again, this first term of MAZ, remember the mass is rho times volume. And so the two-dimensional mass is density, which is gamma over g, times the volume, dx dy dz, or in 2 dimensions, dx dz. So this is the MAZ. And then from the two pressure terms, or the two force terms, if you want to call them that, they result in just dPdZ dx dz, because the P2 dx term cancels in both of these in the second line. So these two come from F3 minus F4, and then this is the weight. Again, weight is specifically times volume. And so as you can see, I've already crossed them out. As always in all these derivations, the volume cancels out because it should never affect what you're going after. So when we cancel out the volumes and resolve or solve this equation for the pressure gradient, just like in the x direction, we solved for the pressure gradient in the x, and that was gamma over g ax. Now what we want to do is solve for the pressure gradient in the z. And what you get when we bring dPdZ to one side and then gamma over g az to the other side, here's the gamma over g az that came from MAZ, the momentum term. And then this gamma term comes from the weight. And obviously we can factor out gamma over g from both of those terms. And what you have then is the pressure gradient in the vertical is equal to minus gamma over g times az plus g. G already has a sign associated with it. G, that G, question?
Where did the G in that last line come from?
This one?
Yeah.
So what we did was take this equation and factor out gamma over g. So if you think about it, gamma over g times g is gamma. Got it? Yeah. I think nicely. So it's just convenient to put it this way. Why? Because az plus g are both accelerations, right? And so it's convenient to see that as we did in the x direction equation, I know you don't have it memorized yet, was minus gamma over g ax. If we had no ax, what do you get? dP dx is 0. You get what happened in fluid statics. I want it in this form because I want to say, well, what if we have no az? We should get what we had in fluid statics. Okay, so fluid statics is just a subset of the general form of acceleration of fluid masses. So this just says that the vertical pressure gradient, and remember, this is how you know this. You know P is equal to gamma h from a free surface, right? You know that. You better know it by now. That is basically from the equation dP dz is equal to minus gamma. The slope of this curve is related to the specific weight of the fluid. And now what happens is, if you have a vertical acceleration, and this is a future slide, you're going to see this in a future slide. If you accelerate upwards, you basically have an effective increase in pressure over and above fluid statics. And if you go down in the elevator, you feel almost weightlessness depending on how fast you're going down. So you see a reduced pressure gradient if your acceleration field is in the negative vertical direction. So that's what we're going to see, but that's basically what this term says, is that now we have the same pressure gradient we were talking about before. P is equal to gamma h. dP dz is minus gamma. That's what we had before. And here's dP dz is minus gamma. That's fluid statics. But now there's this other term because you have an acceleration field other than gravity. And the point I was making before that question was, we've already accounted for the fact that gravity is acting in the negative z direction. So if you use 9.81 meters per second or 32.2 meters per second, you don't need to put a minus sign in front of it. We've already accounted for that. And when I do the examples, you'll see that. So again, gamma over g az is the pressure variation due to the vertical acceleration. So this term, or this term. is again the change in the pressure distribution due to the vertical acceleration, and that other term is our old friend that was the pressure variation just due to fluid statics. And again, that single gamma term that's in the equation above is our old friend, pressure variation due to gravity. So here's our summary. And again, I don't hold you to derivations. This is where we are. We're not at the end yet. So what we found was by looking at sum of forces in the x direction equals 0, is equal to mass times acceleration, dpdx is minus gamma over gax. So all that says is if you have horizontal acceleration, now when you move horizontally, you will be changing pressure. We'll quantify it. The other term, dpdz, is minus gamma over gaz plus g. Again, this is the pressure variation in the vertical. And at the end of the day, if there is no vertical acceleration, we get our old friend, P is equal to gamma h. But if there is some other vertical acceleration, we're modifying that pressure variation in the vertical. And it's modified by how much vertical acceleration you have. The larger AZ is, the more you're changing the pressure distribution. So, if we recognize, and this goes back to your first calculus course, if you ask, what is the total differential or derivative of pressure in this case? A total derivative is the sum of all the partial derivatives. And I just want to go back to the previous slide. This one. Why are we using partial derivatives? Why? Because we're saying that pressure is a function of other variables. It's not just a function of x. It's not just a function of z. But it's a function of, for example, all three spatial coordinate directions, x, y, z. It could be a function of time. It could be a function of something else. So that's why we use partial derivatives, and that's what we did before when we looked at fluid statics. We started in the same place because that's what we assumed. And we just found out that pressure is a function of x and z coordinates if you have this acceleration field. So again, what we're going to say is whatever happened in the x is happening in the y. So we're looking at a 2D derivation. And the other thing we're going to say is we're going to have a time invariant situation. So that acceleration is applied and it just continues. It never stops. And so we can get rid of those two terms in the total differential pressure equation. And why we want that is, remember, just on the last slide, we had expressions for these gradients, dp dx and dp dz. And all we want to do is substitute those in here now. So we're going to look at the two-dimensional form of the total differential of pressure equation. So we got rid of the y and the t variables. So the second line here on this slide is the two-dimensional form of the acceleration of fluid masses equation. And for dp dx is minus gamma over gax. That was the previous slide. dp dz is this term. And so all we did was substitute in for those two terms to get another equation, but we got rid of those partial derivatives. And once we all have simple ordinary derivatives, these equations are really easy to integrate. So for example, we had dp dz is equal to minus gamma a long time ago for fluid statics. And what we did was go from a free surface from point 1 to point 2, and we know at the free surface we could put our elevation datum there, so z is equal to 0 there, and we know the pressure there is atmospheric, 0. And so we would integrate, we would separate variables in this equation and integrate, and ultimately we would get, in this form, P is equal to minus gamma z. Why? Because z is negative as you go down. Z is positive when you go up. And that's why we said, well, let's just get rid of the z-axis that's positive this way and put in an h-axis that's positive that way. So that is how we could identify pressures from one point to another. And I'll get to an example where we actually use this equation. But this equation is not going to be any more difficult to use than P is equal to gamma H. Okay? What you need to know is the fluid properties, specific weight. You need to know the acceleration field. What is AX and AZ? And you need to know how far you're moving in the X or how far you're moving in the Z. Maybe the problem is saying for this kind of a pressure change, how far do I have to move? Or what acceleration field do I have to apply? But it's all the same problem using this equation. You need to have a lot of information to solve this one equation. So this is the pressure change due to movement horizontally, and that term is the pressure change due to movement vertically. And so the total change in pressure now, because you have an acceleration field with X and Z components, the change in pressure has everything to do with how far you moved in each direction, and the pressure gradients in each direction are a function of the accelerations you have. Did you have a question? Stretch. So, what is a line of constant pressure? Obviously, by the name, it's a line of constant pressure. As you move along it, pressure is not changing, right? So, along a line of constant pressure, if you go from one point of that line of constant pressure to another, dP is 0. That's like an elevation contour on a topographic map. If you're on elevation 100 and you keep on walking on elevation 100, you're never changing elevation. dz would be 0, right? So, go back to fluid statics. You've got that glass of beer. Can you identify a line of constant pressure? It's the free surface, right? Everywhere on that free surface, you have atmospheric pressure. And in the fluid static system, where all you have is gravity operating, when you look at any depth below the surface, you have dP dx 0. That line of constant pressure below the surface is also horizontal in fluid statics. And so in a fluid static situation, the contours or lines of constant pressure are all horizontal, right? Now, with the first slide in today's lecture, they're sliding your chocolate milk down the bar, and you know it has a deflected surface. That's still a line of constant pressure, is it not? Of course it is. So, we can look along a line of constant pressure, and I just want to go back. This equation is the equation for pressure changes when moving any direction. I'm taking that equation on the next slide, and I'm setting it to 0. I want to use that equation, but very specifically, I want to employ it just along a contour of constant pressure, and that's why dP is 0. Just think of moving along the surface of that chocolate milk. And so by setting this equation to 0, I've got 0 on one side, and what I can do then is rearrange. So I'll bring that gamma over g ax dx term. You'll see that the minus gamma over g is the same in both of them. First law of mathematics, when in doubt, cancel out. So we just canceled them out. And then we brought the ax dx to the left-hand side. And then after we bring that to the left-hand side, we're going to solve this equation for dz dx, and I will explain why. So in this case, dz dx is equal to minus ax over g plus az. This is our coordinate axis system. Z is positive up, x is positive to the right. Here is that glass of chocolate milk on the first slide. And so we had an AX, bartender was sliding it down the bar, and then the free surface altered from a horizontal surface. And so I'm just going to take this surface and put it in this plane. Okay? That's the free surface on that glass of chocolate milk that you're getting after class. Is that a positive or a negative slope in this ZX coordinate axis system?
Negative.
Negative slope. Everybody agree? Good. I think the people online are a little slow today, but it's Monday. So, what if you look at the equation? Let's say you just had horizontal acceleration, like on the bar. There's no AZ in that case. There's just horizontal acceleration. This says with a positive AX, you're going to get a negative slope, minus AX over G. dz dx is minus AX over G. It's something, again, you saw on the first slide today, and I know you have seen this somewhere before in your life experience. All we did was put numbers to it. So, dz dx is a line of constant pressure. Just like in fluid statics, where the free surface is a line or a surface of constant pressure, and every horizontal surface below it was a line or a surface of constant pressure. Similarly, as you move into this fluid, any line of constant pressure has the same slope. It doesn't say that this has to only be at the surface. It's anywhere in that fluid. If you want to move along a constant pressure contour, it's going to be subscribing to this equation here. So here is that free surface as we identified, and what you see as you move down into the fluid, your contours of constant pressure are parallel to that free surface. They're all parallel to each other. So again, there you have the first slide from today. Did I draw that on there? And so what you have is AX, and you can see how that is sloped. If this is the plus Z plus X direction, it's subscribing exactly to that. So this bartender knew these results before we even went through the derivation. That slide was correct. So along a locus or a contour of constant pressure, this is what we just derived. If AX and AZ are constant, then the lines of equal potential just means pressure or energy, as you will see in the future, must be parallel. That's what we saw in the last slide. So it's not only the free surface, it's anywhere below that free surface, these contours are parallel. And if, before I said what happened if AZ was 0, you only had AX. What if you did not have AX? Well, that equation then says dz dx is equal to 0. So if there is no horizontal acceleration, only vertical, you're taking this beer up and down an elevator, then the fluid surface will remain horizontal, whether it's under an AZ or just G. And I think that's also within your knowledge base of experience. If you take a bucket of water and pull it up vertically, the fluid surface stays horizontal. I expect to see you all doing this at home when you're doing the dishes tonight. Now, there's a unique case. When AZ is equal to minus G, that denominator goes to 0, right? And if you're just thinking without putting reality into this picture, that tells you that the slope should go to infinity. But the real answer is your container enclosed or is it open? If the container is enclosed, then basically you're not losing any fluid, and you will have a pressure distribution within that container. And we'll get to an example. But if the container is open, basically the fluid is just going to leave that container. Right? You're going weightless. Okay, so let's look at very specific cases of applying these equations. And I may only get to one example today, but I'm intentionally going through this pretty thoroughly because we're only building on this as we move through the semester. So we're just going to have vertical acceleration. We're moving something up or down in an elevator. And remember, with fluid statics, that was our equation. We integrated the differential form of the equation, and how we got to this form was we integrated from a free surface where we knew the pressure and the elevation. How did we know the elevation? We set our elevation datum there. we said z is equal to 0 right on the free surface. It's a very convenient thing to do. And so where z is equal to 0, p is equal to 0, and that's how we integrated the equation to get these equations. And then we can move to any other location in the fluid. And so in fluid statics, it didn't matter if we went vertically or to the side because there was no change in pressure moving horizontally. But now if point 2 were to be over here or over here, and you have horizontal accelerations, there's going to be a change. But right now in this context, we're only looking at vertical accelerations. And so we know that for vertical acceleration, dp dx is 0. Remember, dp dx, we just derived this. Sorry, dz dx is equal to minus ax over g plus az. And again, for only vertical acceleration, that's 0. And so you should always have a horizontal surface when you have no horizontal acceleration. So in this case, we're going to start with the original equation. This is our original equation. And we're going to say if we're going to go from point 1 at the free surface to point 2, we're going to apply this equation to find the pressure at point 2. We would integrate this equation from z is equal to z1 to z is equal to z2, which would be, if we say that the elevation datum is 0 at the free surface, z1 is 0. And we're going to go from the surface, p1 to p2. And again, if point 1 is at the surface, p1 is 0. So this integration is really an insult to your intelligence. So here's that form. And again, instead of putting in z2, I wrote in minus z. Because remember, if the z-axis is positive going upwards, and z is 0 at the free surface, when we go from point 1 to point 2 down into the fluid, this z2 is a negative number. That's why I have negative red signs. And again, all of this business comes out of the integration. You're just integrating dp, which is p2 minus p1. P1 is 0. And you're integrating dz, which is just z, and that's z2 minus z1. So when we integrate that and put in our boundary conditions, p1 is 0, z1 is 0, this is our analogy to p is equal to gamma h. What do we have? Well, before we had p is equal to minus gamma z. That's statics. When we did the same thing and the only acceleration field was gravity. Now what we have is this term. And this term is basically a modified specific weight. You're modifying specific weight by the vertical acceleration field you've chosen to add in addition to gravity. So one way of looking at this equation is gamma prime minus gamma prime z, which would be the analogy over here, or again, switch from a z-axis to an h-axis that's positive downward. So it's our old friend. If you had a tank and it was undergoing just vertical acceleration, you could calculate the pressure distribution on that side now with this equation, right? If you knew the pressure distribution on that side, we use pressure distributions for forces on submerged plane objects, right? What is the resultant force on a plane submerged object? It's pressure at the center of area times the area. If you know the pressure at the top and it's linearly changing to the pressure at the bottom, you know the pressure at the center of area, right? So you can calculate the force. It's the same thing. And again, that's the whole place where we're going is we're looking at this case of where we have finite fluid volumes with acceleration fields to calculate forces so that we can design around them. Your challenge would be to identify what should be this acceleration field that I'm designing against. So normally you'll have an expected acceleration field, and then as engineers, we always add a fudge factor, a multiplication term times it, to make sure that we never really exceed it. And then we size, say, the bolts we're going to put on here, or the welds, or however we're restraining the system. So you expect with vertical acceleration, if the vertical acceleration is greater than 0, that's acceleration upwards. Your apparent specific weight is greater than the specific weight of the fluid. And that just means as you move vertically, you're getting more of a pressure change than had that fluid just been static without the vertical acceleration field. And if your acceleration field is negative, meaning that it's downward, the weight of the fluid or the pressures in the fluid are less than on the static sensitive fluid. And obviously, if AZ is too great in the negative direction, then unless you have it contained, the fluid is just going to leave your container. You have it weightless. So in a figure, this was the figure that we had before. These are really ugly gammas. So that's gamma prime, that's gamma H, that's gamma prime. And so basically, when we had just fluid statics, this is how pressure varied as we moved down into the fluid. And then if we have an acceleration field in which the acceleration is upwards, think of it this way. If we had just gravity at this depth, Z, that would have been our pressure. If we had our vertical acceleration upwards, we would have a much higher pressure for that same elevation or distance below the free surface. And conversely, if we had a downward acceleration, we'd have much less pressure at the same location. So what the acceleration field effectively does is change the apparent specific weight. That's one way of looking at it. And that's what these equations are describing. So let's do this example, and then I'll do a more thorough example doing everything, all directions next time. So we're going to have a very simple container, and it's going to have 12 feet of water. And what we're going to do is accelerate it upwards at 20 foot per second squared. And the first question, the very simple thing we're going to act is, what's the pressure on the bottom? So before we do that, we're going to have, again, this acceleration AC is 20 foot per second squared. What we're going to do is ask, well, what if there was no vertical acceleration? How would you have calculated this? You would have said P is equal to gamma H. The pressure on the bottom is the specific weight of water, 62.4 pounds per cubic foot, times the depth from the top, the free surface, to the bottom, 12 feet. That would have been the pressure on the bottom. But now you have AZ of 20 foot per second squared. So when you have that acceleration, what we need to do is use the equation we just developed for vertical acceleration only. We have a more general equation when we have both vertical and horizontal. So the examples I'm going to do is I'm going to look at vertical acceleration only. I'm going to look at horizontal acceleration only in the next example. And then I'm going to look at accelerations in both directions. Okay? So we're just kind of marching through the equation and applying it. So from a free surface, what we did was integrate that equation. dP is equal to minus gamma over GAZ plus G dZ minus gamma over GAX dx. That was our original differential pressure equation, and this is what we reduced it to. And so the pressure at the bottom, this is what we're asking. What's the pressure 12 feet down? So Z is going to be 12 feet. AZ is our 20 foot per second squared. Gamma, specific weight of water. You know everything on the right-hand side. So when we substitute in everything we know, again, specific weight gamma is 62.4 pounds per cubic feet. Acceleration due to gravity, 32.2 foot per second squared. Don't put any sign in front of it because it's already accounted for. Where did that gamma over G come from? It came from the density. When we calculated the density of the cube, we represented it, instead of rho, we represented it as gamma over G. And then AZ plus G, 20 foot per second squared, plus G, 32.2 foot per second squared. We already accounted for the sign on gravity, so don't put it in there as a negative. And then Z, again, Z is 0 at the free surface, and at the bottom of the container, 12 feet down, Z is minus 12. Again, that's from integrating the original equation, yeah.
Could you say that the equation is the same if it was like, instead of z, if it was h and then you got rid of the negative?
Yes, that, if you had done the exact same derivation and had h downward, that would be gone, and this would just be h 12 feet. And that's what we did for statics. That's the direct analogy. And again, fluid statics is just a subset of this. So that would be the effective specific weight. Instead of 62.4 pound per cubic foot, everything but the 12 feet, again, is what I was calling gamma prime. And you can see with upwards acceleration, you have a higher effective specific weight. And now, compared to what we had for statics, now you can see that we've dramatically increased the pressure on the bottom. Yeah.
This might kind of be the same question he asked, but why do you add the 20 feet per second to the gravity if they're in opposite
No,
directions?
you're right. So, when we did sum of the forces equal to max, we accounted for weight. And we said that weight had acted downward, and it was calculated as specific weight times the volume. So we already accounted for the sign when we did sum of forces. And so any more, all you have to do is put in G, no sign. For the accelerations, that's the only one you have to obey, plus x, plus z or minus z. So what would be the force on the bottom of the tank if its area is 3 feet by 1 foot? Well, with no acceleration, this is how we did it before, right? After you have a pressure on the bottom, and we would multiply that pressure by the area of the bottom. Remember, the bottom is 3 foot by 1 foot. So now we have a new force, right? If it was a static situation, you would have that force being offset by a scale. So basically, the force, that vertical force, is the weight of the water. You know that now. And basically, to have this thing sitting there, then the desk or the scale or the ground is pushing up at the same equal and opposite force because the system's just sitting there. In this condition, you have a system that's going up in this direction at AZ. It's got a weight, but it also has an max. So before, some of the forces in the Z, the weight was equal to whatever the supporting reaction force was to hold that system in place. But now, some of the forces is max, maz, and if you multiply this out, you get 3640 pounds, which is what you'd expect. That's what we found up here. So it all comes together. Why? Because that's the way we derived it. It has to come out. If it didn't, we did something wrong. Now, you may find when you're doing calculations, you may be off in that number. And that's probably numerical noise, but the primary number should be the same. So I've run over a little bit. Are there any questions? We're going to pick up on this next time. Online? All right. See you Wednesday.